What's up, y'all? Sean here, and today we're going to talk about the first derivative test. Okay, so all of this is building one video after the other. So you probably want to watch the video I recorded beforehand, before this one, about increasing and decreasing functions if you haven't already. All right, so let's go ahead and get right into it. This first derivative test is as follows. So given that C is a critical number. And if you recall, critical number is a number um, at which a number in the domain of a function where either the derivative does not exist, or the derivative is equal to zero. So it's a point in the domain of some function f of x where if you take the derivative at that point, the derivative is equal to zero, or the derivative does not exist at that point. So given that you have a critical number c, is 2 points. If f prime, so in other words, if the derivative changes from positive to negative um, at c, then the function at that point is a local maximum. So positive to negative, and then this is a local maximum. So if the derivative changes from, and I can't write better than this, y'all, negative to positive at C, then the function at point C is a local minimum. Okay? And then finally, if the derivative does not change signs, there is no local maximum or minimum. Okay? Now, so let's go back through this. If the derivative at this point C goes from positive to negative. So I'm actually going to put a graphic here. And this will make sense in the future. So just imagine, okay, so this is the x-axis, this is the y-axis, but specifically the derivative um, of the original function. And so say you have a derivative that looks kind of like this here. Okay, now keep in mind, this is not the original function f, this is f prime, this is the derivative. Okay, so if the derivative changes from positive to negative, okay, so that's specifically a point like this right here. It's positive, which means it's above y equals 0 here, and then below the x axis is negative. So if it's right here where it changes from positive to negative, this means, so if this, okay, whatever this x value is, let's just call this, um, we'll call this right here A, and we'll call this B. This means that f of B, because so check it out. I'm kind of getting ahead of myself. This is the graph of the derivative. The derivative equals 0 right here. And the fact that it goes from positive to negative means the graph of the original function f at that same point is a maximum. So if you think about that, that means that the graph at this f, if this is the graph of the function and b is right here, that means that right here, so it's positive and then it changes negative. So that this is f. If this is the graph of f, then at point b, then it's changing from positive to negative. See, positive to negative, and then so that means it's a maximum. And similarly, right here, if f changes from negative to positive, which you look right here, it's negative when it's under the x-axis, and then it goes positive. Then that means f the original function at that point, sorry, is a minimum. Okay, and so it basically, you have it going from a negative slope to a positive slope. Okay, and so that's the reverse. So it's a minimum. Finally, if f does not change signs, then there is no local maximum or minimum. Let me kind of erase some of this stuff here. Okay. So yeah, so basically if you have something where it doesn't change signs, there is no maximum min. And so that's probably a situation like if you have the graph of x cubed, which looks like this. Let me put another chart here. So like it's kind of like if you have this situation. So you'll literally have a point in it, if this is f, the original function, f of x, I'll say. At this point here, whenever um, the x cubed graph has that little middle of the s part of it, so to speak, the derivative will be equal to zero because it just kind of goes flat. But there is no change in signs in the original graph here. Remember, this is f of x. This is not f prime of x. But this is a situation where you have a critical number, um, but the derivative of this does not change from positive to negative. It doesn't change signs, if that makes sense. Okay. Now let's apply this to some actual equations. All right. So let's erase this stuff here. Now, really, what you really want to do with calculus, y'all, is you really want to make sure that you're able to visualize it. And I wish there was a way that I could some recording this with this particular tool, then it won't. I can't do like a select all and erase, but it's okay. All right. So now let's apply this to an example. Now, this example is actually one that I did in, I think, the previous video. F of x equals 3x to the fourth power minus 4x cubed minus 12x squared plus 5. And we want to um, find local maximums and minimums. Okay, so what do we need to do? So we need to locate where the critical numbers are. What we're going to do is, basically that means we want to find either where the derivative is equal to zero or where the derivative does not exist. That would tell us where the critical numbers are. So first thing we need to do, step number one, find the derivative. Okay, so that's going to be f prime of x equals, so chain rules, so that's 12x cubed minus 12x squared minus 24x. Okay, now we're going to set, oops, thinking too fast, set the derivative, I'm going to abbreviate a little bit, equal to zero to find critical numbers. Okay, so let's set the derivative equal to zero. So 12x cubed minus 12x squared minus 24x equals zero. We can do some factoring here. So it's going to be, we're going to factor out a 12x. And then that's x cubed. I mean, not x cubed, I'm sorry. X squared, rather. Minus x minus 2 equals 0. We can factor some more. That 12 will divide out on both sides. So it's going to be x times. Now let's factor this quadratic here. So that's going to be what times what is negative 2 that add or subtract to give you negative 1. So that should be x minus 2 and x plus 1. Okay, so this shows you where our critical numbers is. Where our critical numbers are. There is no place where the derivative equals where it doesn't exist. So our critical numbers are x equals 0, x equals 2, and then x equals negative 1. Okay? Now, Remember, since we're trying to use the first derivative test to see where we have local maximums and the minimums, what we want to do is we want to look on either side of the critical numbers to see if it's positive or negative, and then that helps us to kind of see. So I'm gonna make a little chart here. Okay, so we're gonna do this. All right. So where our we want to look again on either side of the critical numbers. If these are our critical numbers here, x equals 0, x equals 2, and x equals -1, we're going to look on either side of those. So we want to look at x is less than -1. Then we want to look at x between -1 and 0. So that's going to be -1, x, 0. Then we want to look at x being between 0 and 2. So 0, x, 2, and then finally x greater than 2. Okay. Now, so let's look at this. So here, remember, here's our first derivative function here. Actually, I want to look at it this way when we factored it. So this is really the same thing as x minus 2, x plus 1. Same thing, okay? Because it's easier to kind of determine to kind of plug in value. Okay, so anyway. So if I plug in a value that's less than -1, for example, -2. Now, what I'm going to do is I'm just going to look at these quickly to see what would be positive and negative because you're not really looking for the value. You're looking for whether or not the value would be positive or negative. So I plug in -2, that'd be -2, that would be -4, so negative and negative, and then that would be negative. So three negatives would make a negative. Okay. If I had a value between 1 and 0, so like -0.5, so that would be a negative. The -0.5 minus 2, that would be also negative, and then this would be positive. So two negatives and a positive, that would mean a positive. Okay. Now, what about between 0 and 2? So like if I plugged in 1, that would be positive. 1 minus 2, that would be negative. And then 1 plus 1, that would be positive. So it's two positives and a negative. This would be negative. And then finally, x greater than 2. So like if x was 3, 3, and then that would be positive. 3 minus 2 is 1, that would be positive. And that would be positive. This would be positive. Now, so we see negative and positive. This is on either side of -1. So you have let me do my hands the right way. So you got a negative slope and then it goes to a positive slope. So that means x equals 1 is a local minimum. Okay. What about this right here represents x equals 0. So x equals 0. So on this side of x equals 0 is positive. So it goes up. Oh, let me see. I'm trying to make my hands go right. So it goes up and then down because it goes from positive to negative. So that means x equals 0 is a local maximum, right? And then finally, we have our third critical point, which is x equals 2. And for x equals 2 on one side is negative. So on the left side is negative, on the right side is positive. Okay, so it goes from negative to positive, so that means this is a local minimum. Okay. All right. So let me know what you think about that. Let me know what you think about that. First derivative test pretty easy. It helps you to kind of start to see even more of the value of the first derivative and how you can use it to kind of determine what your functions look like. Okay, even without graphing the original function. All right. Hey, thank you for watching this video. If you need math tutoring or you need SAT math help, look in the description to find out how you can sign up today. Also, don't forget to like, share, and subscribe so you stay in touch with Math Swap Tutoring on YouTube. Have a good one.